All right, let's talk about one of the heavy hitters in calculus, the chain rule. And trust me, this isn't just for passing exams. It's the engine that powers everything from physics simulations to how artificial intelligence actually learns. It's the key that lets you differentiate all sorts of complex, nested functions. So let's dive in and pull back the curtain on it.
So you're probably feeling pretty comfortable finding the derivatives of basic functions, right? But what happens when those functions get stacked inside of each other? Well, that's a whole different ballgame, and it creates a really interesting challenge.
Okay, so check this out. You know how to differentiate sine x? No problem. It's cos of x. And you can differentiate x cubed? Easy. That's 3x squared. But what happens when you smash them together and get sine of x cubed? All of a sudden, our basic rules don't quite cut it anymore. We need a new tool for the job.
What we're looking at here has a name. It's called a composite function. Think of it like a set of Russian nesting dolls. In our example, you have an outer function, the sine of x, and an inner function, the x cubed, that's tucked right inside of it.
Now, before we even touch the official formula, let's just think about this intuitively. The name chain rule is actually a fantastic clue. It really is like a chain reaction. So think about it this way. When you nudge the value of x just a little bit, it doesn't just instantly change the final answer. No, first, that nudge causes a change in the inner part, the x cubed, and then that change ripples outwards, triggering a change in the outer sine function. It's like a domino effect.
And that right there, that's the whole secret. To find the total rate of change, which, remember, is just the derivative, you have to account for the rate of change at each link in that chain. And how do you combine them? You just multiply them together.
So that intuitive idea of a chain reaction leads us straight to the formal rule. Let's take a look at how calculus writes this down precisely. Okay, I know this looks like a mouthful, but don't worry. It's saying exactly what we were just talking about. You take the derivative of the outside function, but, and this is the crucial part, you leave the original inside function alone right where it is. Then you multiply that whole thing by the derivative of the inside function. Now you're going to see this rule written in a couple of different ways. Over on the left is prime notation. It's clean, compact, and it's probably what you'll use most of the time when you're solving problems. But on the right, you've got Leibniz's notation. I actually love this one because you can literally see the chain reaction. See how the du terms seem to link up and cancel out? They're just two different ways of saying the exact same thing. All right, enough theory. Let's put this thing to work and finally solve that problem we started with.
Okay, let's break it down into its pieces. Our outer function is sine of u, and its derivative is cos of u. Got it. Our inner function is x cubed, and its derivative is 3x squared. Got it. Perfect. We have all our building blocks ready to go.
And now we just assemble it. We take the derivative of the outside, which is cos u, and we plug the original inside function back into it. That gives us cos x cubed. Then we just multiply by the derivative of the inside, which was 3x squared, and there you have it. That's our answer. One thing you'll find out pretty quickly is that the chain rule almost never works alone. It's a real team player. You'll constantly see it pairing up with the product rule, the quotient rule, and especially with its best friend, the power rule. You know, this combination is so common and so incredibly useful that it's often taught as its own special case. Whenever you have some function, any function, raised to a power, this is your go-to move. It's a powerhouse.
Let's run through a quick example. For this function, the outside part is the power, the -2. So we apply the power rule first. Bring the -2 down in front and subtract 1 from the exponent. But then, and you can't forget this part, the chain rule kicks in. We have to multiply by the derivative of the stuff inside the parentheses, which is 6x.
So, you're probably wondering, what if the nesting gets even crazier? What if you have a function inside of a function inside of another function? What happens then? Well, here's the beautiful part. It's not a new rule. The pattern just continues. You just keep adding more links to the chain. If you have 3 nested functions, your derivative will have 3 parts multiplied together. 4 functions, 4 parts. It extends perfectly, no matter how deep you go. Okay, so with all these potential layers and moving parts, what's the best way to remember all this and get it right every single time? Well, the key is to have a simple, repeatable process. So here it is, your 3-step game plan. Step 1, identify your layers. What's the outermost function? What's inside it? Step 2, differentiate that outermost layer. But, and this is the part people sometimes forget, just copy the inside stuff over. Don't touch it yet.
Finally, step 3. Multiply that whole result by the derivative of the next layer in.
I like to think of it as peeling an onion. You start with the very outer skin, deal with that, then move to the next layer in, and so on, until you reach the very center. You always work from the outside in.
Look, if you remember nothing else from all of this, remember this one sentence. This little mantra perfectly captures the entire process. It is the absolute heart and soul of the chain rule.
So you see, the chain rule isn't just some formula you memorize for a test. It's a key. It unlocks the ability to understand rates of change for a massive new world of functions. It's how physicists calculate how a rocket's distance and angle change together. It's even the mathematical core of how neural networks learn. A process called backpropagation is basically just the chain rule, applied thousands of times. So, now that you have this incredibly powerful tool, what are you going to do with it?